A warm welcome to the first video in the third chapter of Crystal Clear Electronics 2. In this part, we will explore the basics of low-level programming, we will review the necessary knowledge, and show you how a microcontroller instruction set is constructed. We will also point out two widely used microcontroller architectures, the x86 and the ARM. Our presenter today is Dr. József Domokos, an electronics and telecommunications engineer and lecturer at Sapientia University. He oversees the Crystal Clear Electronics Study Group activities at the Farkasbolyai Secondary School in Targu-Mureș, and he also teaches digital electronics and communication theory at the university.
I also welcome our viewers. Thank you for the introduction and the brief overview of the video content. The third chapter is actually called Low-Level Programming in C language, the process of compilation. In this chapter, we try to provide an introduction for those who want to learn about programming microcontroller systems in low-level hardware. At the same time, we'll also review why some programs can run on some computers and not on others. We'll examine why we can generally use the C language for developing embedded devices, despite the differences in the internal architecture of the processors. The chapter was written by Zsolt Tamó and proofread by Ádám Szabó. My partner will be Mária Schuster, who worked for several years in the automotive and electronics industry in the fields of quality and laboratory. She's currently working as a teacher in the electronics industry.
That's right, thank you for the introduction. Let's get started with today's chapter. As we have already seen in the 10th chapter of Crystal Clear Electronics 1, each programmable operation execution unit has a so-called instruction set or instruction set architecture, which defines the instructions that the processor can execute. Softwares or programs are composed of sequences of these instructions, which are called machine code.
Instruction sets can be used to describe even the most common activities. A fun example of something we all do is the process of making bread with margarine. In this case, the unit of the operation is the human making the bread with margarine. The operands on which the operations are performed are the margarine, the bread, and the knife, while the instructions are grab, slice, unwrap, spread. Then the machine code for the program to make the bread with margarine looks like this. The first instruction is to grab bread. Then grab knife. Then comes a two-operand operation, the slice, bread, and knife. The next step is the unwrap margarine, the grab knife, and the last operation is the spread margarine, bread, knife with three operands. The bread with margarine is ready. It can be seen that not all of the operations can be executed on all ingredients. For example, the instruction slice cannot be performed on the margarine, since the margarine is a spreadable and not a sliceable substance. Thus, the instruction set is more than a simple list of instructions, since it must also specify on which input or inputs the instructions can be executed and where this information is located. For example, the instruction unwrap margarine makes sense and can be executed if the margarine is already on the table, but not if it is still in the fridge. When we write a program, whatever programming language we use, the ultimate goal is to turn the program we write into a sequence of codes that can be executed directly by the processing unit, that is the machine code. This transformation between programming languages and machine code is called compiling.
The significance of defining the architecture is that by merely defining and fixing the instructions that the processor can execute, circuit designers can design a useful circuit without knowing the user program, and conversely, software developers can write program code without even knowing the specific circuitry of the processor.
The chosen instruction set will of course have a big impact on what the microcontroller can be used for and how efficiently. On the one hand, it allows processor manufacturers to ensure backwards compatibility for the software if their newer models use an existing instruction set architecture. That is, they can execute the same instructions as the previous model. On the other hand, several models with different performances or even from different manufacturers can and do use the same architecture, making it easier for software developers to port the software from one to another microcontroller. The instruction set architecture basically defines three things. The first is the effect of the instruction. This means that a change occurs after the instruction is executed. For example, an add instruction causes a sum to be created somewhere, or a jump instruction changes the value of the program counter. The second is the operands of the instruction. This is the data needed to execute the instruction. For example, in case of an add instruction, the operands, that is A and B numbers to be added for A plus B, and the new memory address for jump instructions. The third is the supported data types for operands. The information needed to understand operands, how many bits they are stored in, and the encoding, integer or real, signed or unsigned for numbers.
The parameters of the instruction must be written in binary form along with some rule or scheme so that the machine code can be understood by the CPU. In an embedded environment, an important consideration is the amount of memory the encoded program takes up. The efficiency of different architectures can be compared in terms of code density. The higher the code density, the less memory space is used by the machine code.
Generally speaking, to perform arithmetic operations, these are the basic operations such as addition, subtraction, multiplication, and division. It is sufficient to specify three operands, two inputs of the operation, and the register or memory address. But there are solutions where the result or even the input parameters are stored in a fixed, predefined location. With these, the encoding of the instruction is simplified, and the encoded length of each instruction can be reduced since fewer operands are required. However, at the same time, more instructions may need to be executed, as these fixed locations can be filled with separate instructions to load the data to be used, so it is not clear which solution is more efficient in terms of code density. The two most common criteria for grouping instruction set architectures are whether, for arithmetic operations, these operands can be registers only, or possibly memory addresses too, and whether the encoding of instructions has fixed or variable width.
To understand this better, let's look at a simple example with two widely used architectures. One is the x86 and the other is ARM.
Let's start with the x86 architecture. This architecture became widespread with the appearance of Intel's 8086 processor. Nowadays, most computers are based on this architecture. In the case of the x86 architecture, we find that the machine code is quite complex. Even the length of instructions is not the same in all cases, varying from 1 to 16 bytes. As we can see, a part of the machine code, in this case the first 1 or 2 bytes, is called operation code or opcode. This part encodes the logical effect of the instruction. The opcode can be found in all instruction set architectures, not just in the x86. In order to keep the opcode unambiguously decodable despite the variable length, in the case of 2-byte length operation code, the first byte contains a predefined value so that the theoretically possible 2 to the 16th opcodes are already limited to 256 by the architecture. For example, 9 opcodes can be used to add integers without carry, depending on the operand specified. The following table summarizes the add instructions with the different types of operands that they can be used with. The result of the operation is always stored in the first operand's position according to x86. In the table, lowercase r refers to a general purpose register, r per m refers to a general purpose register or memory address, and IMM refers to the constant value encoded in the instruction. The numbers indicate the width of the operands in bits. The AL, the AX, and the EAX are the names of the specific registers. Since the operands of arithmetic operations can be stored in registers or in the memory, the x86 architecture is a register memory architecture.
The second presented architecture is the ARM. The microcontroller we use in this curriculum supports the thumb instruction set. It implements a subset of the instructions of the ARM architecture. ARM stands for the English term Advanced RISC Machines.
ARM instructions are encoded in 32 bits, but the smaller instruction count of thumb has allowed the most common instructions to be encoded in only 16 bits, allowing a higher code density, so that in general, the machine code for the same program is shorter with thumb than with ARM encoding. Each 16-bit thumb instruction can be matched by a 32-bit ARM instruction, so that the central processing unit performs the same steps for both instruction sets after a conversion.
Although there are microcontrollers for which this conversion can be set, the Cortex-M cores that we use can only interpret the thumb format.
In the ARM architecture, both the operands of the arithmetic instructions and the result can only be stored in registers. A separate subset of instructions is used to move data between memory and registers, so ARM implements a so-called register-register, also known as load-store architecture. This is where the name comes from, that the read, load, and write, store from memory are implemented as separate processor instructions and well separated from arithmetic or logic operations.
When comparing the two architectures, what conclusion can we draw?
Since operands in a register memory architecture can come from multiple sources, this type of architecture typically allows many more valid opcode operand combinations, i.e. machine code, than a register-register architecture. Processors using this architecture, including the ones implementing the x86 architecture, are therefore called complex instruction set computers, or CISC for short. In contrast, ARM processors following the load-store architecture are classified as reduced instruction set processors, which we call RISC, or Reduced Instruction Set Computer Architecture.
Thank you for your answer. This brings us to the end of the video. In the next part, we'll learn about assembly and C languages, and we will look at some code snippets. Until then, have a nice day. Bye!
Bye!